Hello everyone, I am Lianggang Shichen from East China Normal University. Here is a video for introducing our paper, Clip-Driven Open Vocabulary 3D Single Generation via Cross-Modality Contrastive Learning. At first, I will introduce the difference between our method and the previous methods. This figure shows difference in training. Previous 3D single generation models trained on closed set classes by fully supervised. Our method trains a 3D single feature extractor on naturally collected image text pairs without using any 3D single labels. And the difference in inference. Previous 3D single generation models failed to recognize novel class, limiting its practice in real-world scenes. Our model can recognize novel objects and predict classes. And here is our pipeline. We propose the CCL 3D single generation architecture, and this architecture begins with inputting image text pairs and unlabeled 3D point clouds, aiming to train the 3D single feature extractor p-theta. We explore part-of-speech analysis and enhance negative samples in the test. Subsequently, the text is proposed by text encoder t-theta of clip to obtain text feature ft. The T3D loss aligns text with 3D single features. Multi-view images are fed into image encoder I-theta for clip to extract image feature fi, and the I3D loss aligns image with 3D single features. In the inference stage, well-aligned 3D single features FP are facilitated to predict novel 3D single classes in real-world scenes. Specifically, during the training phase, we use clips, text encoder, and image to extract text and image features. At the same time, we decompose the text into subject, object, predict, adjectives based on the part of speech. Next, for two different triples, we exchange their adjectives to form negative simple argumentation. After obtaining three modal features, we use cross-modal contrastive learning loss to align the image and text with the 3D single features and train a robust 3D single feature extractor. Okay, finally, after training the 3D single feature extractor, we use the designed prompt words for classification. For example, for object class classification, we use a point cloud of object class. Insert the object class blank. For predictor class classification, we use a point cloud of a subject class, predict class, object class, predict class to insert empty spaces. Okay, so let's talk about our experiments. Our method can be extended by modifying the loss to the following form. And here we compared our method with other 3D single generation methods that use recall and averages recall metrics. That is mean recall. Our method outperformed the previous model in both texts and improved by 20% compared to the method in chapter. And despite introducing additional information, our model achieved significant performance improvements from 24 to 30 without significantly increasing time overhead. Our method achieves state-of-the-art art performance for predictor classes at the tail and on-C triples. These results confirm that our model provides a more robust 3D singular feature representation, enhancing its generalization ability to on-scene triples. And the above image shows 4 challenge scenes from various indoor rooms, including bedroom, living rooms, and bedrooms. This shows that our model can distinguish between easily confused objects and predictor aspects, such as books, and leaning against. The cross-view I3D loss enhances the model's ability to distinguish special predicts such as in front of and behind. It is worth noting that our model addressed the language bias observed in previous models by transforming the predicted representation of building to a more accurate predict attached to. Meanwhile, previous methods were all supervised and had very poor performance for unsupervised text, mainly because they were designed solely for supervised purpose and lacked lossless functions. Our method achieves SOTA under unsupervised text by carefully designing unsupervised constructive losses. And finally, we use 70% of the objects and the predict classes in the 3D graph generation dataset for training, known as the base classes. Our goal is to effectively identify the remaining 30% of new objects and predict classes during the inference process. A combination of 17% of base and 30% of new classes. This is called Open Vocabulary 3D Scene Graph Generation task, as well as only 30% of new classes. That is called Zero-Shot 3D Scene Graph Generation task. We have achieved SOTA results in the generation of 3D scene graph in Open Vocabulary and Zero-Shot. Thank you.